Hello, welcome to part 3 of lecture 11. I'm going to be covering union, intersection, and complement of events. Um, some of the stuff will be a little bit familiar to you from chapter 7 when we're talking about union, intersection, and complement. So I'm going to go through this part relatively quickly. The probability aspects of it are very similar to what we covered above, which is basically, and I'm going to review quickly the most important part of that, and that is that the probability of an event. So the probability of E is equal to the number of elements in the event divided by the number of elements in the sample space. So when you're calculating probability, this is kind of what to remember. The number of elements in the event divided by the number of elements in the sample space. And that's just as true when we are talking about union, intersection, and complement. And you'll see that very shortly. I'm going to turn my view off. There we go. Um, and a lot of times I'm going to be referring to this chart as well when I do some of these things, just so you know. So if you've got one of those available to you, great. Anyways, when we're talking about probabilities, we're talking about a couple of different things. And this is, like I say, very similar to what we've already seen in regards to intersection and sets. So this first one represents a union. So this is A or B. So every element in A or in B. So an element if it is in A or if it is in B. And we already know how that works. And then the intersection, it has to be in both. And we know that this last one, we know that they're disjoint. So there is no intersection, so they're disjoint. If you were to do the intersection, it would be the empty set. And if we were to do the union, it would cover both A and B. The language, again, is for a union, the language we say or. So when you see a word problem, it has or in it, it's talking about a union. If it has and in it, it's talking about an intersection. And recall when we were talking about sets, when you were doing a union, you had the union of the events. So when we were in sets, when we would do the number of elements in the union of A and B, it was equal to the number of elements in A plus the number of elements in B minus the number of elements in A intersect B. We don't want to count this part twice. So that's why we're doing that. And the exact same thing is true when we're doing probabilities. So the probabilities, if we know the probability of A and we know the probability of B and we know the probability of the intersection, and those things we can calculate using our number of elements in the event divided by the number of elements in the sample space. We have this. And of course, if they're disjoint, the intersection is 0 as the empty set. And then an important concept in probability when we're calculating probabilities, and this gets used regularly, is the probability of a complement is equal to 1 minus the probability of the element itself. And a lot of times when we're calculating probabilities, we're going to do something along these lines. So let's take a look at what we got. So, what is some examples? What is the probability that a number selected at random from the first 140 positive integers is divisible by 4 or 6? So we know that the sample space is 140. There's 140 integers. The number of integers, so it has to be an integer, it has to be a whole number, divisible by 4. Well, we just divide 140 divided by 4, and that equals 35. And hopefully these are. So 140 divided by 4 is equal to 35, and 140 divided by 6 is actually equal to 20. And 140 divided by 6 is actually equal to 23.33, but it has to be an integer, and 24 integers is not, so 23 is the correct answer for number of integers. So now we have n of a, n of b, and what we're interested in is the union. So what we need to know is the intersection. So how many integers are divisible by both? Well, how many integers are divisible by 24? How many? So 140 divided by, that's the least common denominator, right? So, I'm sorry, the least common multiple of 4 and 6. Yeah? Or 12. 12. 12 is the least common multiple. So 140 divided by 12. And there are 11 integers that are divisible by both 4 and 6. So actually, what I have here is incorrect. What I'm doing now is actually correct. So I'm going to quickly mark this as incorrect, and we'll come back to this, because this is wrong. Because the least common multiple is 12. So now we have the probability of A union B is equal to the probability of A, go up above, plus the probability of B minus the probability of A intersect B. And now we're just going to use our numbers. So we have A is 35. 35 divided by 140 plus 23 divided by 140 minus 11 divided by 140. And that gives us, let's see, 35, 58, so 47. 47 divided by 140. 47 divided by 140, which is equal to 0.3357. So what is the probability that a number selected at random from the first 140 positive integers is divisible by 4 or 6? And that probability is 0.3357. As I indicated, this is incorrect. So from the previous example, what is the probability that an integer divisible by 4 is not selected? So recall that the probability of an event, not an event, is equal to 1 minus the probability of the event. Well, that would be 35 over 40. That's this one right here. So it's 1 minus 35 over 140. So that would be equal to 105 over 140. And that is 105 divided by 140, which is 0.75. 0.75. Okay. We're going to do another one. This is example 3 on my page, but it is homework number 25. So, with a random selection, excuse me, with a random selection from 25 balls numbered 1 to 25, what is the probability that the number drawn is odd or a multiple of 4? Okay, well, what we can say, well, let's work our way through it. So, what is the sample space? The size of the sample space is equal to 25. There's 25 balls, so that equals 25. What is the n of A? That is, how many elements are in, how many elements in this are divisible by 4. So that would be 25 divided by 4, which is equal to 6. It has to be a whole number because there aren't balls that are 6 1/4. So then we have the probability of A is equal to 6 divided by 25. And then we have the probability odd. So odd. Half of them are going to be odd. In this case, if you count it out, if you actually count it out, you'll go 1, 3, 5. So you're going to have odd and then plus 1. So then the number of elements that are odd is equal to 1, which equals 13. And then the probability of B is equal to 13 divided by 25. And then we have to consider what is the intersection of A and B. So the intersection is those that are both odd and multiples of 4. Well, there is no intersection. So we can say since the intersection A intersect B is equal to the empty set, we know that their probability is 0. So the probability of A intersect B is equal to 0. In that case, we have that the probability of A union B, which is odd or a multiple of 4, is equal to 6 divided by 25. And I should say divisible by 4, or I mean a multiple of 4 or odd, plus 13 over 25, which is equal to 19 over 25. And I would just leave this in that form. And we'll do another example. So far we've demonstrated union both disjoint and with an intersection and also a complement. And now we'll kind of do more of an application problem and show you how to set that up. So we have a shipment of 45 precision parts, including 9 that are defective. It's sent to an assembly plant. The Quality Control Division selects 10 at random, so it just randomly selects 10 for testing and rejects the entire shipment if 1 or more samples are found to be defective. So what is the probability that the shipment will be rejected? So the event is 1 or more parts in a random sample of 10 are defective, right? So they select 10 of them, and they just want 1 that's defective, 1 or more. Now, when we say 1 or more, that clues us in a little bit. So E is the event that 1 or more are defective from 10. When we say 1 or more, there's a couple ways we can look at it. We can check, if we're checking 10, that means you can have 1 that's defective, 2 that are defective, 3 that are defective, 4 that are defective. So usually we don't calculate it that way. We're not going to do that addition. It's usually easier to just say, so what is the event that none are defective? And if we choose the event that none are defective, the opposite of that, if none are defective, the opposite of that, the complement of that, is that 1 or more are defective. So in this case, instead of calculating E, we're going to find not E. None are defective. Okay? So we have a sample space, and our sample space is, we're choosing 10. So N. So N of S. Looking at this, I want to make sure that I say this right. We're choosing N of S, which is we're choosing 10, selects 10 from 45. So N and R is equal to 45, choose 10, and that's a number. And then we want, there are 9 of them that are defective, so we cannot select one of those 9. So we want that none are defective, so then the number in E0 is equal to N, like still 45. No, it's not 45, is it? No, of course not. So it's 45 minus 9, right? So do you understand why we're doing the minus 9? So we're taking out the defective parts. So then we want to know how many ways can we choose 10 parts without selecting any that are defective. So 45 minus 9 is 36. 36, choose 10. And that is our event space. So this is the size of our event. This is the size of our solution. And then our probability of not E is equal to, let's just calculate it using the calculator, 45. So 36, choose 10. 36, choose 10 divided by 45, choose 10 is equal to is equal to 0.07967, and then the probability that one or more are defective is equal to 1 minus the probability that none are defective, and that equals 0.920, which is rather high probability that at least one of them will be defective. If you are interested, look into the birthday problem. I believe it's written up rather extensively in the book, but it's an interesting problem. It basically goes over in a room with so many people, how many people in the room have the same birthday as you, and at a certain, you'd be surprised how quickly the probability gets up pretty high that somebody has the same birthday as you. We'll save odds for one more lecture. So stop recording.